Hello dear learners, in this lecture we will discuss another problem, and that problem is 0-1 knapsack problem, which we have earlier discussed using dynamic programming, but this time we will solve it using branch and bound algorithm. So let us recall what is the 0-1 knapsack problem. So we have in this problem a thief who is trying to rob a store, and he has a knapsack in which he can carry a maximal weight that is equal to capital W, and in the store there are n number of items which are available, and we are also given the weight of each item and the profit of each item, right? The thief wants to pick the items in such a way that he gets the maximum profit, right? So this is our problem scenario, and this is 0-1 knapsack. Another variant of the knapsack problem is fractional knapsack. In 0-1 knapsack, the thief does not have the option to break an item into fractions. He can either pick the item or leave the item, right? But in fractional knapsack problem, the thief has the option to break the item into fractions. Okay. So we are given an array profit of which has the profits of all the n items starting from 0th item to n minus first item. Similarly, we have another array weight which is storing the weights of all the n items, and as I told you earlier, we have a number W which gives us the maximum capacity of the knapsack, and our objective is to find or pick the items in such a way which maximizes the profit. But the constraint here is that sum of weights of the items should be less than or equal to the profit of the weight of the knapsack. Okay, and also the profits and the weights are the positive numbers. Okay, so there are a number of approaches which we can use to solve this problem. So let us look at those approaches one by one. The first one is greedy approach. In the greedy approach, we can pick the items in the greedy manner, that is in the decreasing order of profit by weight ratio. Means first pick the item which has the maximum profit and the minimum weight. Okay, so this strategy works only for the fractional knapsack problem, as we saw in the lecture in which we solve the fractional knapsack problem, right? And we saw there that the same approach which we use for the fractional knapsack problem, it cannot be used for 0-1 knapsack problem. It may produce incorrect results, right? Okay, let us go to the second approach, that is dynamic programming. Dynamic programming works well for the 0-1 knapsack problem, but the restriction or the limitation of this approach is that this does not work if the item weights are not integers. It works only if the item weights are integers. Okay. Now let us move to the third approach. The third approach is simple brute force approach. In this brute force approach, we create a state space tree, right? So we start at the root. At the root, we pick the first item. For the first item, we have two possibilities, and from there on we go to the next level and we explore all the possibilities for the second item, and so on. So for each item there are two possibilities. Okay, so this will result in a tree which will look like a binary tree, right? And in this brute force approach, we will check to see if the branches in the tree, they satisfy the constraint. What is the constraint here? The constraint is weight of the knapsack should be less than or equal to the capacity of the knapsack. Okay, so we have the number of solutions. We enlist all the possible solutions in the brute force approach, and then we sieve those solutions through the constraint. Okay, so we keep only those solutions which satisfy this constraint, right? And out of those solutions, out of those sieved solutions, we save the maximum solution, right? Maximum solution means which maximizes the profit. Okay. The limitation of brute force approach is that the search space is exponential, right? All the brute force approaches are exponential. They need exponential time to execute. Okay, so in order to cut short the time, we can go to the next approach, which is called backtracking. Backtracking can be used to optimize the brute force solution. In backtracking, as we have done a number of examples of backtracking, you might recall that we go in the depth first order, right? And when we reach a node where we see that the constraints are not being satisfied, we backtrack and we then search for the next solution and so on. Okay, so here how the brute force approach is optimized using backtracking. Backtracking prevents exploring the nodes which do not lead us to a solution. Okay, so in this way we are able to minimize the time required for the execution of the algorithm, right? And the last approach which we will use in this lecture is called branch and bound. Here we can do better than backtracking if we know a bound on the best possible solution subtree rooted with every node. Okay, so as you might remember, in the previous lecture on branch and bound, that was on the job assignment problem, we used a bound. At every node we calculated a bound. The bound can be an upper bound or a lower bound. Upper bound is used in maximization problems and the lower bound is used in the minimization problems. Okay, so at every state we check this bound. This bound helps us to know whether this node will lead us to the best possible solution or not. Okay, so if the best in the subtree is worse than the current best, so we compare all the live nodes. Okay, so among all the live nodes we pick whichever is the best. Okay, so if in this subtree there are a number of solutions, okay, so if this is the best and if this is the best in this subtree but this is worse than the current best, suppose this is the current best, then what we will do, we will ignore this node and all its subtrees, right? So this is how we will go in this 0-1 knapsack problem using branch and bound. Okay, so let us now look at this example of 0-1 knapsack problem. In this example, the weight of the knapsack is 16 and here we have n equal to 4. We have 4 items. We are given the profits of each item and the weight of each item, and we have also calculated the profit by weight ratio. Okay, so profit by weight ratio of the first item, for example, is 45 by 3, that is 15. Okay, so now we can start creating the search space. Okay, so let us start with the root node. So here initially the profit which we have earned is 0 because we have not put any item into the knapsack, and also the weight of the knapsack is 0. Okay, so these are the two things, plus we have to calculate a bound, and because this is a maximization problem, we have to maximize the profit, so we will find an upper bound. Okay, so how do we find an upper bound? This is a mixture of 0-1 knapsack plus the greedy approach to the fractional knapsack problem. So let us see how. So the upper bound is calculated by looking at the items one by one. So let us look at the first item. Okay, so the first item's weight is 3. Okay, and the capacity of the knapsack is 16. So we can pick the whole first item. Okay, so if we pick the whole first item, then the profit which we earn will be 45 and the remaining weight is 13. Okay, so now let us move to the next item. The next item's weight is 5 and the profit is 30. Okay, so weight is 5 and the knapsack capacity is 13, so we can pick it. Okay, so if we pick it, the remaining weight, it will be 8 and the profit will be, total profit will now be 75, right? Okay, so now let us look at the third item. In the third item, the weight is 9 and the profit is 45. Okay, so the weight of the third item is 9. We cannot, now we will use the fractional approach to just find an upper bound. Okay, so it means we cannot pick this item completely. We have the weight of the item is, for example, 9 kg, but we have the capacity of 8 kg in our knapsack. Okay, so it means out of 9 units we can pick only 8 units. Okay, so similarly the profit will be for 8 units, not for 9 units. Okay, so profit will also be 8 by 9 of 45, so it is 40. Okay, so now the capacity of the knapsack is 0 and the profit, total profit is 115, right? Okay, so this is our upper bound. Okay, so this is our upper bound. So this is the best, current best, and this is a live node. It means we have visited or touched this node. Okay, now because this is the only node, we will explore this node, so this now will become our E node. Okay, so E node is the node whose children are being explored. Okay, so here this E node will have 2 children. It means here we will look for example, let me name these items. This item is x1, this item is x2, this item is x3 and this item is x4. So at this level we will consider the first item x1. Okay, so x1 can be 1, x1 can be 0. x1 equal to 1 means we are taking this, we are picking this x1 item. x1 is 0 means we are leaving this item. Okay, so when x1 is 1, we reach this node. So this is our live node now. Okay, so when you pick this item, then profit will be 45, weight will be 3, right? And what will be the upper bound? Upper bound will be the same as we calculated in the previous step, because here we considered the first item, right? We added the weight 3 and the profit 45 of the first item. After picking the first item, there was a room left for the second item, so we picked the second item, whole of the second item, and then after picking first and second item, we could pick only 8 by 9th of the third item. Okay, so by picking the items in this order, the total profit, the upper bound on the profit was 115. So it will be 115 only. Okay, so now let us go here. When we do not pick x1, okay, now this is our live node, This is also a live node. Okay, so if we do not pick this item, we are not putting anything into the knapsack, so the profit will be 0, weight will also be 0. Now the upper bound will change. We are not picking the first item. Okay, so let me erase this so that I can write the entire thing here. Okay, so upper bound, we are not picking the first item, so leave it. Go to the second item. The second item's weight is 5 and the profit is 30, right? Weight is 5, profit is 30, and we can pick the whole of second item. After picking this item in the knapsack, the capacity left will be 11 and the profit will be 30, right? Then we go to the third item. We can pick the third item because its weight is 9. After picking, still we will have the capacity of 2 in the knapsack. So if we pick it, the profit which we get will be 45, right? Now let's go to the fourth item. Fourth item's weight is 5. We cannot pick all the 5 units because we have room for only 2 units. So out of 5 units, we can pick only 2 units. So the profit here will be 2/5 of the total profit. The total profit is 10. Okay, so it will be total 79. So this is the upper bound. Okay, now out of these 2 live nodes, the least upper bound which we are having is on this node. The most or the maximum upper bound, because this is a maximization problem. Okay, so we will explore this node. Right now this node will become our E node. We will explore this node. So this level was about x1. Now this level is about x2. X2 can be 1, x2 can be 0. Okay, so it means when we pick x2, then what will happen? Now this is a live node. If we pick x2, the profit will be the previous profit, because we reached here, we reached this node from its parent, this node. Okay, so it means after picking x1, now you are trying to pick x2, right? So it means profits will be added. The profit of x1 is 45 and the profit of now x2 is 30. 45 plus 30, the total profit will be 75 and the weight will be 3 plus 5, 8. Okay, and what will be the upper bound? Upper bound will be the same as above, because in the above calculation we were picking x1 and then whole of x2 and some fraction of x3. Okay, similar thing we will do here. So upper bound will be 115. Okay, now let us see this option. Now this is our live node. Here we are not picking x2. So we are not picking x2. It means the profit will remain same as the previous node. Nothing will be added. So it will be 45 only. Weight will remain 3 only. And upper bound, now let us see what will be the upper bound. So here we have reached after picking x1. So the weight of x1 was 3 and the profit was 45. Okay, so the remaining capacity of the knapsack was 13. Now we are not picking x2. Let us move to x3. x3 we can pick. Okay, its weight is 9, its profit is 45. Okay, so after picking, the capacity left will be 4. Now let us move to x4. x4, its weight is 5 and its profit is 10, but the knapsack capacity is 4, so we can pick only 4 units. 4 by 5. Profit will also be 4 by 5 of the total profit. Okay, so it is 8. So total profit is 98. Okay, so upper bound is 98, right? Okay, so now out of these 3 live nodes, which will become our E node? E node will be the node with the maximum upper bound. So this node will be explored further. Now this level will deal with x3. x3 can be 1, x3 can be 0. Okay, so let us see what happens when x3 is 1. Now it means we are picking x3. When we pick x3, let us see, we have reached here after picking x1 and after picking x2. So the weight is 8, right? The total weight is 8. And then if you pick x3 also, the total weight will be the previous weight plus the weight of this item. This item's weight is 9. So the total weight will become 17. But the capacity of the knapsack is 16. So it means we are not able to satisfy the constraint. We are violating the constraint. So this results in a dead node, right? So this node will not be explored further, right? This is our E node which we are exploring now. Okay, so now this has resulted in a dead node. Let us explore the second child of E node. This is when you are not picking x3. So when you are not picking x3, the profit will remain the same as the parent node, that is 5. Weight will also be 8. And what will be the upper bound? Okay, let us go there. So the total weight is 16, and we have reached here from x1 equal to 1, x2 equal to 1 and x3 equal to 0. x1 is weight is 3, profit is 45, x2's weight is 5, profit is 30. So we can directly copy from this parent node also. Okay, and x3 we are not picking, and for x4 what is its weight? x4's weight is 5. Okay, and it means we can pick the whole of x4, because if we pick all these items completely, then the total weight will be only 13. So which is less than the capacity of the knapsack, right? And profit is 10. So the total profit is 85, right? Upper bound is 85. So this is not profit actually, this is only a upper bound, because we are considering the fractions of the items here, but actually only we can pick the item or we can leave the item. Okay, so this strategy is used, the fractions are used only to compute the upper bound, right? Okay, so this is now our live node. This is also one of the live node. Okay, so this is a dead node, we will not consider this. And out of these live nodes, which are the live nodes, this one and this one, we will explore the best one. Okay, so this is not the best, so we will not explore it further. This is the best out of all these live nodes, so we will explore this node, right? Okay, so when we reach this node x3, now again the same decision, it can be 1 or it can be 0, right? Okay, so this is now not live node anymore, this is E node. Okay, and these two nodes will become our live node. This is also a live node, this is also a live node. Okay, so here x3 is 1, it means we are picking x3. So when we are picking x3, then it means profit, the previous profit plus the new profit, it will be the total profit. So previous profit is 45 and we are picking x3, so 45 plus 45, total profit will be 90. And weight, the previous weight is 3 and weight of this item is 9, so the total weight will be 12. And now what will be the upper bound? So here we reached from this node, so we can directly copy the profit and the weight. The previous, at the parent of this node, the profit was 45 and the weight was 3. Okay, so now we are picking this item. It means its weight is 9 and its profit is 45. We can do this. Okay, and do we have still some room left? 3 plus 9 is 12, so we can take 4 units more. Okay, for the next item we can pick 4 units, so 4 by 5, and the profit will also be 4 by 5 of the total profit. Okay, so 4 by 5 of this, it is 8, right? So the total profit is 98, right? So this is the upper bound. Now let us move to this node. Here we are not picking x3, so the profit will remain the same as the parent, weight will also remain the same as parent, and upper bound, the previous upper bound is 98, previous upper bound is 98. Okay, so the profit was 45 and the weight was 3. Okay, and x3 we are not picking, so we can pick x4. x4's weight is 5 and x4's profit is 10, right? So total it is 55. Okay, so 55 is the upper bound. Okay, so now out of all these live nodes, so this we have explored. Okay, so the live nodes are this node here, and this one, and this one. Okay, so out of these 4 nodes, let me mark them with a different color. Okay, so this one is a live node, and then this we have explored. This one is a live node, this one is another live node, and this one is another live node. So out of these, the maximum upper bound is at this node where x3 is 1, so we can explore this node now. Right. So here we will take a decision about x4. x4 can be 1, x4 can be 0. Okay, so when x4 is 1, we are picking x4. Okay, so previous weight is 12 and x4's weight is 5, so the total weight will be 12 plus 5, that is 17. So now we are violating the constraint here, so this will not be explored further, this will become a dead node, right? Okay, so let us explore. This is not live node. Now this is a E node. Okay, so now the second option is x4 is 0. If it is 0, then profit will remain the same as its parent, that is 90. Weight will also remain the same as its parent, that is 12, and the upper bound, we are not picking this item. Okay, so I think the upper bound will also remain the same. The previous upper bound is 98 and now the last item is x4, so there is no item after this, so upper bound is 98, right? So now this is the solution to this 0-1 knapsack using branch and bound. So what is the solution actually? How to extract the solution? So here we ended, right? So it means x4 is 0, and who's the parent of this node? This one, right? So it means x3 is 1, and who's the parent of this node? This one, right? x2 is 0, and the parent of this node is this one, where x1 is 1, right? So the solution to this branch and 0-1 knapsack problem using branch and bound is that you pick x1, leave x2, pick x3, leave x4. Okay, so the total profit you will earn is 45 and its profit is also 45. Profit will be 90 as written here, and the weight will be 12, right? So this is how we can solve this 0-1 knapsack problem using the branch and bound algorithm. Thank you.